talk on Stokes waves, continuing, I guess, in the thread of the previous two talks. So Vera, floor is yours.
Thank you. Thanks to the organizers for inviting me to be part of this very special occasion. So this talk is related to the positive waves, and in fact, Darren and Mark both effectively stole some of my thunder, but that's okay. Also, I know like many of you in the audience have heard some versions of this talk before, but if I choose and I chose to speak about this because this is what relates me to John Mark. As you see, like I got Vanderpool number one on this problem. And also, like we have a group of with the diverse background here, so maybe this is new to the. So here we go. By Stokes waves, I mean periodic traveling waves, the free surface of water in two dimensions and infinite depths of possibility. The motion is acted on by gravity, and I'm going to ignore surface tension for today. So imagine water waves like in this photograph. Now, this is a very, very old problem going back to Stokes in the 1840s something, and it's also a very famous problem. You can read about this even in Wikipedia. It is traditional in this problem to collect your solutions in a bifurcation diagram that you see on the left. So on the horizontal axis, we measure the wave amplitude, or more precisely, the stiffness. What that means is the crest to trough vertical height divided by the wavelength. And on the vertical axis, we're going to measure the solution either using an energy or even using the wave speed, because each solution has its own speed to travel with. Now, if you collect all the solutions, then you form a solution curve, either cyan or all the other different colors, and each point on this solution curve will represent the free surface on top of the water that you see on the right. Now, for zero vorticity, it has been well predicted and also partly proved that as you increase the stiffness or amplitude, then crest becomes sharper and troughs flatter. And the so-called wave of greatest height will have a sharp corner at the wave crest with a 120 degrees angle. Moreover, the wave speed and all the other quantities that are shown here, they oscillate. They are predicted to oscillate infinite many times towards this extreme wave, making this problem very, very hard. Now, some recent advances in this problem, both analytical and numerical, are based on the reformulation of this problem to the Babenko equation that you see here in the box. And for those of you who are not familiar with the Babenko equation, I have to say that this is not a simplified model equation. This is a reformulation of the full Stokes wave problem, which is to solve the Euler equation in the Fourier fluid and together with the two non-linear boundary conditions at the fluid surface. There is no approximation goes into this equation. Now, this is clearly a non-linear equation and also non-local. Here, the script H, the Hilbert transform, and it can be defined as a Fourier multiplier operator. What's behind this equation is that you conformally map your fluid domain, so like the domain underneath this surface, from a lower half plane. Okay? So that if it is conform mapping, then the horizontal and the vertical components of the fluid domain will be related to each other through the Hilbert transform. And that's why you see here the Hilbert transform in this formulation. Now, but vorticity is important, as we already appreciate from the previous two talks. Vorticity is important even without free surface in fluid mechanics, and it is true even with free surface. Now, for arbitrary vorticity, this is now almost a 20 years old result that Konstantin and Strauss, they established the global bifurcation result. That means that you have a connected set of solutions connecting zero amplitude solutions all the way to large amplitude solutions. But they had to assume that there are no overhanging profiles in the collection of solutions they found, and there are no interior stagnation points. But for zero vorticity, one can prove that in fact there cannot be any overhanging profiles and there should not be any interior stagnation point. So you don't have to impose these properties. But for non-zero vorticity, even in the simpler case of constant vorticity, and even for small amplitude, you can construct analytically solutions with the curve of interior stagnation. Now, more recently, Konstantin, Strauss, and Babaruka, they redid the global bifurcation analysis, now for only constant vorticity, but instead allowing overhanging profile and interior stagnation point. And they conjectured that the solution curve, a solution curve that found is going to be limited ultimately by an extreme wave with angle at the crest with or without overhanging profiles, or else you should find a a touching wave that you see on the right, whose profile will bend to touch itself at the trough line and trapping an air bubble. But this is actually very major contributions to this subject, but the proof is very non-constructive. For example, they were not able to say that these overhang profiles exist in the solutions they find. So our initial goal in this project was numerically compute the results to see what happened. And of course, we're not the first to numerically computing with constant vorticity. One of the earliest contributions were by Simon and Stockman in the 1980, 1985. And subsequently, this result is in the infinite depth case, and subsequently, Perez-da-Silva and Peregrine, they extended this result to the finite depths. And of course, many people in this room, they contributed to this problem and a policy not doing the justice to the history of the problem. Now, Simon and Stockman, the collective solution in the wave speed versus the stiffness plane. And you see this little curve, tiny curve here. This is to produce the zero vorticity result. Okay? And for negative vorticity or like a downstream case, then the curve is getting shorter. That means the extreme waves are shorter. But otherwise, the result is qualitatively same as the zero vorticity case. But for the opposite sign of vorticity, for upstream case, there are some important differences you see. So for example, like one thing is that for large in a positive vorticity, you see that the stiffness increases and decreases and increases again. A corollary of this is that this extreme wave is no longer a wave of greatest height. And also, if the vorticity even larger, for example, here, then the solution curve breaks up into two pieces and it creates a gap. And by the way, Simon and Stockman called this profile as a fold. So you're supposed to see two new features, fold and gap. And I'm going to explain what's happening at the fold and the gap later using my own result, our result. And in the 90s, Jean-Marc proposed a different way of looking at this problem. So he started with this extreme corner wave and systematically decreased the gravitational effect, and then found all kinds of these weird looking waves. And I think it was now almost 6 years ago, there was a semester program on water waves at ISERM. And Sergey and I were visiting Brown and ISERM for the whole year, and we're intensively working on this project. And one of the embedded activities in that semester program was the 60th birthday conference for Jean-Marc. And actually, at that birthday conference, I learned about this result from Paul's presentation. And this really inspired later when, again, I found something like this. We're like, oh, this is what Jean-Marc found. So actually, like this guided us to navigate this problem. So this is my Jean-Marc story. Okay. All right. Now, Jean-Marc and Simon Stockman and also Perez-da-Silva and Peregrine, they all use the reformulation of this problem into some boundary integral equation. That has been the traditional approach, and our approach is to reformulate this problem into some Babenko-like equation. So this is our formulation. This is, so what I want to say is, even including constant vorticity, still the Babenko equation looks quite concise. Okay. Now here, all these terms are written in blue. They are involved with the constant vorticity. Now I'm going to call that little omega. And if you drop all these blue terms, then you go back to this original Babenko equation. And a solution to this Babenko equation gives rise to a Stokes wave with constant vorticity, provided that these two bullet points are satisfied. Now, if the first one fails, then you get a touching wave. And if the second one fails, then you have a singular solution, and that seems to imply that you have an extreme wave. Now, without further ado, I'm going to explain what we numerically find and how you see all these waves that Darren and Mark were showing. All right, so our starting point is when omega is 2, and we chose this value because this value is larger than those values that the Simon and Softman computed with confidence. So we started to go to where Simon and Softman stopped. Now, on the upper left corner, this is a C versus S plane, and this green curve is supposed to be green. This green curve is a solution curve. And on the right and the lower left, these are free surface that you see in the physical plane, XY plane. And we collected these points in the various places, locations along the solution curve. Now, along the left side of the fold, as you increase the stiffness, what happens to the solution is that the profile becomes more and more rounded. So that at point B, you have a touching wave. And if you pass that touching wave, then your solution looks like this. And while the function that describes this blue curve is a perfectly fine solution to the Babenko equation, but if we were to be a water wave solution, then what that means is that you have a fluid region overlapping with the neighboring ones. So this is unphysical, right? Nevertheless, you can continue to solve this solution mathematically. And now, like on the other side of the fold, when you decrease the stiffness, then the profile becomes now less and less rounded, so that at some point, like point E, you have a touching wave again. And beyond this touching point, then the solution becomes physical again. So in summarize, the gap is made up of all these unphysical solutions, and they are bounded by two touching waves. Okay. Now, beyond this lowest point of the fold, then the amplitude or stiffness increases monotonically, but the wave speed oscillates, as you see this in sets. And while this is going on, the crest becomes sharper, as you see here. So the behavior is similar to the zero gravity, zero vorticity case. Now, at this point, I have to say that the numerical method of Simon and Softman, it breaks down, it diverges in the gap. And then how do they find the other piece of solution curve? Well, they assume that this solution curve will ultimately end at a extreme wave at the stagnation point at the wave crest. And they solve that boundary condition to locate the end point, and then to continue backward until they have to stop again. And this idea would work if there is only one gap to this problem. So there is no physical solutions between these two touching waves. And it turns out that there are more than one. So for example, when omega is 2.5, then you have two folds and two gaps. And what happens along the first fold and first gap, the same as before. And along the second fold and second gap, qualitatively the same, but except that these waves have two bulbs. And while you stop there, you continue. So as you increase the value of vorticity, then you increase number of folds and gaps. So for example, when omega is 4, then you have 5 folds and 5 gaps. And now each gap here is bounded by two touching waves. And this is a brand new phenomena that didn't exist for zero vorticity case. Right? So this is interesting. So that's why we decide to look at this case more closely. So now on this left panel, I collected those touching waves at the beginning of the first gap with the different values of vorticity. And on the right, these are touching waves at the end of the first gap. Now, as we increase the vorticity, And by the way, this is the same as decreasing the gravity. Then on the left, so as we increase the vorticity, then the stiffness of these waves takes the limit, and the limiting stiffness is approximately 0.7 right? And on the right, at the end of this gap, the limiting value is 1. That means the wave height is same as wavelength. Moreover, it seems very obvious that the limiting shape is perfect circle, right? So it seems clear that the infinite vorticity limit of these waves are this fluid disk in this body rotation. What's happening on the left? Well, by the way, these waves resemble one of Jean-Marc's waves. Now, at this point, this is not surprising anymore, but nevertheless, so Kepler in his 1957 paper, he wrote down exact formula that solves the capillary wave problem, and I'm presenting his formula. Basically, this is a rational function with the one pole in the complex plane. So it's no surprise. But if you have a formula, then you can do pretty much whatever you want to do. So you can plot all these solutions. And what you see is that the limiting wave is a touching wave instead of a corner wave that you see in the Stokes wave case. And this limiting stiffness is approximately 0.73. And well, so I discovered this as by accident because we were stuck for a while. We didn't know what this limiting wave means. And then we decided to look at something else. So we wanted to look at the capillary gravity wave problem. For that, we wanted to look at the limiting case, the Kepler wave. And then this number seems awfully familiar. So we went back and we plotted. Now this dotted curve is actually plot of this limiting Kepler wave. And you see this agrees very well with the large vorticity, the touching wave. So we thought that it is not completely unreasonable that the limiting scenario of this problem is, and it's shaped in the limiting wave. Then I explained this to Jean-Marc, and he pointed out correctly that, well, not just this limiting wave, but all the other Kepler solutions, they must be a solution to this zero gravity problem because they are all coming from this one family of function, only bearing the parameter A. So we provided some evidence to that. And then later with Miles, we were able to prove that, in fact, this Kepler's formula, it solves the constant vorticity problem with the zero gravity. And when I say we proved, well, so we did the most naive thing. So here is a solution and there is an equation. So you plug in and you check. We didn't do any fancy thing that Darren did, but if you need an A proof, then I think that's fine. So that's the proof. All right, and then this is an old result, right? And in the beginning, we found that this Kepler thing. We were wildly excited. I posted again, very wildly excited, and we thought that there must be something going on between vorticity and surface tension, right? This must happen for a reason. We thought that, and we tried to find why this is happening, and we haven't found any good explanation. Why one should expect this? Why it's happening? And now, if you're asking me, I think it is a miracle. There are things that we should still find the exact solutions in case number 3. I'm not sure. It's not clear to me. I would like to put some efforts to that, and I think this Kepler solution is so simple. So it can happen in different places for no reason. I think it's pure luck. Another reason that I think that this is a coincidence is that the fluid dynamics is completely different, right? So for the capillary wave problem, these free surfaces are streamlines. So in particular, all these streamlines are open, but it is not the case for constant vorticity problem. Nonetheless, this is a good finding, I think, that makes already like finds some applications. And one application we found, I found with mice is that, so we have exact solution for zero gravity. And then now we can perturb this solution with a small gravity because the gravity fact is of lower order in the equations, right? And then you can find a solution to gravity waterway problem with constant vorticity nearby these exact solutions. In particular, you can find overhanging and touching waves with gravity and constant vorticity, which was conjectured in the paper of Konstantin Strauss and Babaruka. And so now we have a proof of that some of these waves do exist. So that's one application of this finding. Now, so if you continue, right? Now on the left, these are touching waves at the beginning of the second gap. And on the right is the end of the second gap. And as you see now, the limiting configuration on the left side is this perfect circle on top of Crapper. And on the right is a perfect circle on top of another perfect circle. If you continue, then you see this. Now, so what that means is so vorticity 4 or larger, we know that there are at least 5 pores and 5 gaps. And these are touching waves at the beginning and end of gap number 1 through 5. And these green curves are for vorticity 4, and these yellow ones are for vorticity 14. And vorticity 14 is our kind of a large vorticity limit. So as you see that when you move to the next gap, you put another circle on top of the solution previous gaps. And in theory, you should be able to stack as many ice cream cubes as you want to or you need. All right, so now with the remaining time, I want to say a few words about how this solution curve will end. So our preliminary pneumatics suggests that no matter what your vorticity is, these curves should be ultimately ending at a corner wave. And if there's an angle, I think there is a proof that this angle should be 120 degrees. But as I say, when you approach this extreme wave, all these guys are oscillating very, very rapidly. So it is not trivial to take. So we need to look into a little more. Now, so back to zero vorticity case. For zero vorticity and for extreme wave, there's a proof that the solution is convex down. Now, actually, I could put up this one so I can draw something. So for zero vorticity for extreme wave, then there's a proof that the solution at the profile is convex down between two consecutive wave crest. So that the angle, if we consider angle that a point, a tangent makes with the horizontal, then the maximum attains at the wave crest, and this angle, I'm bad with the drawing. This angle is 30 degrees and it's decreasing. That is known result. So it came as a surprise when Longy, Higgins, and Fox, they predicted that if you're talking about non-extreme wave, then this angle can be bigger than 30 degrees. And in fact, if you're close to almost extreme wave, but not extreme wave, then this maximum angle takes a limit, and the limit is 34.7. So it just slightly exceeds 30 degrees. And then the fact that the maximum angle can be bigger than 30 degrees was proved by McLeod about the same time. Now, Chandler and Graham in the 90s, they numerically computed this angular business in some detail. So here, I don't think this is very visible, but their paper was printed in a bad low quality. So I couldn't do anything better than this. So on the left, so this is on the vertical axis, this is the angle in degrees. And on the horizontal axis, this is effectively the horizontal axis x-axis, but in a log scale from the crest to trough. Okay? And so now these are the these are the plots of the angle for 3 different almost extreme waves. And as you're marching closer to this line, then you're getting closer to your extreme wave. Okay? So what you're supposed to take it from here, so, of course, these are not yet the extreme wave. So the crust is flat, right? So the angle starts from 0, but then there is a boundary layer near this crust where the angle sharply rises to this maximum angle 30.37. And then the angle oscillates around the 30 degrees, and these oscillations are too tiny to be visible in this scale, so they had to plot separately. So here, this is the first max angle, so you get 30.37, and then first the local minimum, and second local maximum, and the second local minimum. And the size of these oscillations drops like a factor of 100 as you move to the next extreme value. And this oscillation resembles somewhat Gibbs phenomenon. And after this oscillation zone, then there is outer region where the angle drops monotonically down to 0 at the trough. So the way, like what this suggests is that the way that the waves approaches the extreme wave is very, very non-trivial. And during the pandemic, Sergey and I were not able to visit each other. So we decided to revisit this angle business because we have a code, so we just calculate, right? So we decided to do that. And then we learned that in order to have this fine detail, then we need to compute things right. So it took us like 1 year to fix our code so that we can compute these. But then this is our result. So we basically computed. So we computed that this angle business. So on the top, it's the same as before. So this is angle versus the log of x. Okay. And on the left panel, this is the vorticity +1. And on the right is a vorticity -1. And as you see, near the crust, the behavior is the same, right? There is this boundary layer. And then what you see on the bottom is the oscillations of these waves, these angles. So the near crust behavior is the same for whatever the vorticity is, right? And moreover, what we computed is, so we computed how this maximum angle changes as we get closer and closer to the extreme wave. So like on the horizontal axis, we measure how you're close to this extreme wave in the log scale. And then on the right is the difference of your angle. And this yellow curve is vorticity +1, and the green curve is vorticity -1, and red curve is vorticity 0 vorticity. And what we see is these angles monotonically converges to this limiting value. And this is in contrast to all the other values like wave speed and energy. All the other quantities, they oscillate, right, to take this extreme value. But these angles, they seem to be monotonically approaching the limiting value. But then like we found that these first maximum angle and the first local max and first local minimum angle, they are to be independent of whatever the vorticity is. Now, then what's the effect of vorticity? Well, first thing is this, right? For positive vorticity, then in the outer region, the angle shoots out far above 30 degrees before it settles down to 0 at the trough. And with our limited numerical experiment, we never found this angle to be exceeding 90 degrees. That means these profiles are not overhanging, but our numerical evidence is not very strong, so I'm not going to bet on my money on that. And another more subtle effect of vorticity is, well, so what this suggests is that, at least in the leading order, the vorticity does not have any influence right, describing near crust behavior. But it does come into the next order because it changed the curvature. And because of that, we have to calculate, we have to get much closer to the extreme wave to resolve many oscillations. So in order to, so like when we are closer to, when you're closer to the extreme wave, to the like 10 to the -18, whatever that means, then we are able to resolve 3 oscillations. And with this value for 0 vorticity, we can resolve at least 6 oscillations with accuracy. So that's the effective vorticity. And the last thing I want to say is, as I said, come back to this oscillation. So wave speed oscillates infinitely often, right? And and that oscillation seems to be also universal. Doesn't depend on the vorticity. And in fact, we can write down the asymptotic behavior, and the frequency is given by what the Longe-Higgins box calculated. And this screams out to some theorems. So if for people who are proving theorems in the audience, I think this is a good problem to give a proof. And with that, I think I'm done with my time. So here are some references, and thank you for listening.